The aggregation window state machine manages the lifecycle of temporal data buckets within the streaming pipeline. Each window maintains an internal state representation that transitions through defined phases as data arrives and processing thresholds are met. The state model consists of 5 enumerated values: open, pending seal, sealed, flushing, and archived. Transitions occur deterministically based on wall clock time, event count thresholds, and explicit flush signals from upstream operators. The open state represents an active window accepting new events. A window enters open when its wall clock interval begins, or when it is instantiated during stream consumption. The maximum residence time in open is configurable via the window max duration parameter, measured in milliseconds since window creation time. During open state, the window accumulates events in an in-memory map structure keyed by aggregation dimensions. No persistence operations occur in this phase. Transition from open to pending seal occurs when any of 3 conditions is satisfied. Elapsed time exceeds window max duration. The event count within the window reaches the event count threshold parameter, or an explicit seal signal is received from the control plane. The transition is atomic with respect to concurrent event insertions. A mutex-protected check ensures no race conditions during state change. Once pending seal is entered, new events are rejected with a window closed error code. The pending seal state is a transient holding phase that permits in-flight events to complete their aggregation operations. The duration of pending seal is bounded by the pending seal timeout parameter, which defaults to 30 seconds. During this phase, read access to the accumulated state is permitted for late-arriving events within the grace period. After timeout expiration or explicit commit signal, the state machine advances to sealed regardless of pending operation count. The sealed state indicates that no further event modifications are permitted for the window. At this point, the aggregation map is finalized and read-only. The state machine performs a final consistency check. It verifies that all pending aggregation operations have completed or been discarded. If any operations remain pending after the consistency check interval, they are forcibly terminated and logged for audit purposes. The window is now eligible for serialization. Transition to flushing state is initiated by the persistence layer when it determines that the serialized window payload should be written to durable storage. The window state is serialized to the format specified by the aggregation output codec configuration parameter. Common codec options include protobuf, Avro, and JSON delimited. During flushing, the aggregation map remains locked to prevent concurrent modifications. The serialization process does not hold the lock for the entire duration. Instead, a snapshot copy is created and released. The serialization snapshot includes metadata fields: window start time as milliseconds since epoch, window end time, aggregation dimensions, the aggregated metric values, event count within the window, and a checksum computed via CRC32 of the payload. The output record is enqueued to a bounded output queue with capacity controlled by the flush queue max size parameter. If the output queue reaches capacity, back pressure is applied upstream and no new sealed windows transition to flushing until queue space becomes available. The persistence layer acknowledges successful write completion via a callback invoked by the storage backend. Upon acknowledgement receipt, the state machine transitions the window to archived state. This transition is idempotent. If a duplicate acknowledgement is received, the state remains archived without error. The acknowledgement callback also triggers the deallocation of in-memory structures associated with the window. The total memory footprint for the window is released to the heap memory manager for reuse by subsequent windows. The archived state is a terminal state. No transitions occur from archived except for eventual garbage collection. Windows in archived state are retained in a registry for a configurable retention duration specified by the archive registry TTL parameter. This registry permits lookups by window identifier for late-arriving event classification and trace debugging. After the retention period expires, the window entry is removed from the registry and the associated metadata is discarded. Periodic cleanup runs every 60 seconds by default. State machine edge cases are handled deterministically. If a window receives a seal signal while in pending seal state, the seal operation is acknowledged and the timeout is immediately triggered, advancing to sealed. If a flush signal is received while in open state, an immediate transition to pending seal occurs. If any signal is received while in archived state, the signal is silently dropped. No error conditions are raised for these edge cases. They are treated as normal operational scenarios. Metrics and observability instrumentation record state transitions via event counters. The metrics aggregation window transitions total increments whenever a state transition occurs, tagged with source state and target state label pairs. The gauge aggregation window active count reflects the current number of windows in open state at each sampling interval. The histogram aggregation window residence time MS measures the total time from open to archived for completed windows, enabling performance analysis of window lifecycle overhead. Configuration of state machine parameters is accomplished via the aggregation config YAML section. Parameters window max duration, event count threshold, pending seal timeout, flush queue max size, and archive registry TTL are all configurable at initialization time. These values cannot be modified during runtime. Changes require a graceful shutdown and restart of the aggregation engine. Configuration validation occurs at startup and logs warnings if derived values conflict, such as when pending seal timeout exceeds the total processing timeout. Memory overhead per window is bounded and predictable. The base window structure consumes approximately 256 bytes regardless of dimension cardinality. Each aggregation dimension consumes 8 bytes for the dimension key hash and 6 bytes for cardinality metadata. The aggregation map consumes memory proportional to the number of distinct dimension combinations present in the window. Typical windows with moderate cardinality consume between 10 and 50 kilobytes of heap memory during open and sealed states. Concurrency model utilizes a single state machine lock per window instance. Acquisition of this lock is required for all state transitions and for the serialization snapshot operation. Lock contention is minimal in typical deployments because lock hold times are brief. The critical sections are bounded to transition validation and metadata updates. Lock acquisition uses a non-blocking trilock pattern with exponential backoff for retry logic, preventing priority inversion on the state transition path. Recovery procedures for incomplete windows follow a deterministic protocol. If the system crashes while a window is in flushing state, recovery identifies the partially written payload via the durable transaction log. The incomplete payload is discarded and a new flush operation is queued. If a crash occurs during pending seal, the window is automatically transitioned to sealed upon recovery. Windows in open state at crash time are discarded. Their events are not replayed unless the upstream event log provides replay capability. The aggregation window state machine is designed for operational stability and minimal manual intervention. State transitions are fully deterministic. No operator decisions are required during normal operation. Alarm conditions are triggered if the archive registry exceeds capacity or if mean window residence time increases beyond 110% of the expected baseline. These alarms serve as early indicators of downstream pressure or configuration drift. The state machine implements no automatic remediation. Administrative review is required for parameter adjustments.